All right, 1210. We were working on this worksheet for Unit 5. We had gone through all of the one-step and two-step conversions. Remember, we're using units to guide us in these conversions. Now looking at percent compositions, we're still going to be taking advantage of some of these conversion steps, but to give us different types of information. We looked at question number 7, where to find the percent carbon in the sample, we took the 108 grams divided by 174 grams, multiplied by 100. Plug this into our calculator. And we can round here because there's not a lot of significant figures that are really emphasized in this question. Can round to about 3 significant figures. Doing the same thing, we can find the percent composition for hydrogen, 18 grams over the 174 gram sample times 100. Notice that when I'm doing these calculations, I am still putting in the units, and that tells me that the units cancel, which is good because I'm trying to get a percentage. I'm not trying to get any units in here. Percent oxygen, 48 grams over 174 gram sample. Times 100, 27.6. Just rounding to 3 sig figs. I know that if we were being more rigorous about sig figs, we'd be limited to 2, but this problem isn't necessarily focusing so much on sig figs. All right, straightforward when we know the mass of the entire sample and when we know the mass of the individual things. But what about when we're given something generic like this? Well, we're given the chemical formula, more or less. We can derive the chemical formula. That gives us a total. The total is the molecular mass of water. That's twice the mass of hydrogen plus the mass of oxygen for a total of 18 grams per mole. And we know the mass of just oxygen is 16 grams per mole. So I might not have specific mass values to work through here, but I now have these molar mass values that I can plug in. Percent composition is part out of the whole times 100. Once again, I'm plugging in units just to be safe, but I notice that grams per mole cancels on both sides. If I round my answer, I get 9 point. Sorry, plugged in something wrong there. Times 100, 88.9% composition oxygen. Once again, we have to do the same thing for magnesium nitride. We need to figure out the chemical formula first. Magnesium is always a +2 ion. Nitride here is a 3- ion. We can determine that using the periodic table, recognizing that nitrogen in group 5 likes to take on 3 extra electrons in order to become like a noble gas. That gives nitrogen N3- charge. We can do the box method or we can do the crisscross method. What we find our chemical formula here will be Mg3N2. Now I want to know the composition of nitrogen in Mg3N2. There are 2 nitrogen atoms in Mg3N2, which means, unlike before where I just took the molecular mass of 1 oxygen, I now need to take the molecular mass of both nitrogens. So I can set this up as 2 times 14 grams per mole as my part divided by 2 times 14 grams per mole plus 3 times magnesium's molecular mass, 24.3 grams per mole. I'm not multiplying by 100 yet. I'm just finding these values. So the part nitrogen is 28 grams per mole. Out of the entire system, 28 plus 3 times 24.3, 100.9 grams per mole. Now I'll multiply by 100 when I take this ratio. (27.8% nitrogen). Moving on to empirical formulas. Remember that empirical formula is simply the lowest ratio, the lowest whole number ratio of elements in a chemical formula. So we don't know that the empirical formula is the chemical formula. There are 2 different ways that we get the empirical formula: when we're given masses and when we're given percentages. Mass is 1 step shorter than percentage. We're going to take these masses, 11.17 grams of iron and 21.27 grams of chlorine. And our first step is to convert those masses into number of moles. So we should actually set this up much like we did on the front page. I need to cancel units of grams of iron, and I need to get into moles of iron. And in the same way, I need to cancel grams of chlorine, and I need to get into moles of chlorine. You'll notice that these units are the molar masses. Iron's molar mass, 55.85 grams in 1 mole. Chlorine's molar mass, 35.45 grams in 1 mole. 11.17 divided by 55.85 gives me 0.2 moles of iron, and 21.27 divided by 35.45 gives me 0.6 moles of chlorine. Step number 2 is to divide by the lowest number of moles, and in this case I'll be dividing by 0.2. You'll notice I'm not putting units here, I'm actually just dividing by that number. 0.2 divided by 0.2 gives me 1 mole of iron. 0.6 divided by 0.2, number gets larger, I get 3 moles of chlorine. Now, step 3 is to just write the chemical formula, the empirical formula, as long as these are already whole numbers. So let's look at Fe1Cl3. That's our empirical formula. And we know this as iron 3 chloride, which means this is also likely our chemical formula. Okay, when we have percentages, we need to take 1 step further. We have to take these percentages and say that we have a sample of 100 grams. Now the percentages become the mass in grams. We also want to take this 1 step further. We're no longer going for the empirical formula. We're going for the chemical formula. In order to find a chemical formula, you have to be given a molar mass. You must be given a molar mass to compare to the empirical mass. So, step 1, take these percentages and convert them into grams. 40.4 grams of carbon, 7.9 grams of hydrogen, 15.7 grams of nitrogen, and 36.0 grams of oxygen. Again, assuming we have a 100-gram sample. This works great for us. Step number 2. And I realize up here I probably should have been labeling these as step 2, step 3, step 4, which goes along with how we followed those steps in our notes. We're skipping step 1 because it's already in grams. Here we're following step 1. Once again, I'm going to set up my conversions to cancel grams of these elements and get into moles of these elements, which means that I need the molar mass of each individual compound here, each individual element. Carbon weighs 12 grams per mole, hydrogen weighs 1 gram per mole, nitrogen weighs 14 grams per mole, oxygen weighs 16 grams per mole. You'll notice that in my calculations, I'm actually rounding from the periodic table. I'm not putting 12.01, I'm not putting 14.0067, I'm not putting 15.9994. Rounding gives us close enough approximations that, especially on multiple choice problems, allows us to just write simpler numbers and get close enough to find the multiple choice answer. 40.4 divided by 12 gives me 3.367 moles of carbon. 7.9 divided by 1 is 7.9 moles of hydrogen. 15.7 divided by 14 is 1.12 moles of nitrogen. And 36 divided by 16, 2.25 moles of oxygen. Step 3, divide by the smallest number of moles. In this case, that's the number of moles of nitrogen. So I'm going to divide every number by 1.12, just setting them as a ratio to get to a whole number easily. 3.367, I'm actually going to go back into my calculator and reselect this number, just so that I don't have to lose anything from the rounding. And I say that, but I actually didn't even grab the 1.12 correctly in my calculator. You can see no matter what I do, I'm going to have to round. I'm not writing 3.002123144. I'm going to round this to 3 because I'm looking for a whole number of moles of carbon. 7.9 divided by 1.12, 7.05. I'm going to round this down to 7 moles of hydrogen. 1.12, of course, becomes 1 mole of nitrogen. And 2.25 divided by 1.12, I'll round this to 2 moles of oxygen. I do want you to notice, even though my numbers had 2 or 3 significant figures, I'm getting them down and just removing significant figures here because I'm looking for whole number values. Step number 4, put these together and write the empirical formula. C3H7NO2. And this has an empirical mass, 3 times 12 plus 7 plus 14 plus 2 times 16. The empirical mass here is 89 grams per mole. To find the chemical formula, I need to find the ratio between the molar mass of the compound and the empirical mass. In this case, the empirical mass and the molar mass are the same value, which means they're a ratio of 1. This is the empirical formula and the chemical formula. Now, let's say that our molar mass was something like 267 grams per mole. Well, now my empirical mass and my molar mass are not the same. So I take the ratio. Notice how in these conversions the units cancel. So I'm left with a simple ratio, not necessarily a unit of measurement. 89. You know what? I apologize. I flipped these numbers. This should be 267, the molar mass, grams per mole, divided by 89 grams per mole, the empirical mass. 267 divided by 89 gives me a whole number ratio of 3. My molecular mass is 3 times higher than that of my empirical mass. So my empirical formula needs to be multiplied by 3 in order to get the chemical formula. 3 times 3 gives me 9. 3 times 7, 21. 3 times 1, 3. 3 times 2, 6. I've used this ratio as a multiplier on my subscripts to give me the new chemical formula. Okay, our other worksheet was on concentrations, module 13. We worked through this one in class, and we saw that in order to find the molarity, which is moles per liter, we needed to take the mass that we had here and use the molar mass to convert this into moles. We did this all in one step, but we could have done this in 2 separate steps. We could have showed this as 4 grams of sodium hydroxide being converted from grams into moles using the molar mass. I get something here, 0.1 moles of sodium hydroxide. Now that I know this, and I know the number of liters, I can simply divide them and I get a concentration, 0.1 molar NaOH. 2 steps, but to combine them, all you need to do is add on an additional step here where you divide by 1 liter. In question 13, we do have unit of molarity, but we don't necessarily find ourselves up here in our conversion factor, because what we're looking at is concentration of sodium nitrate and concentration of nitrate. That's concentration of A and concentration of B, but we never know a volume. We need volume if we're ever going to move between concentration and moles. So I can rewrite molarity as 1.5 moles of sodium nitrate per 1 liter. Now I don't need to know the volume. I can just leave volume as it is, and I can instead show a mole ratio between moles of sodium nitrate and moles of nitrate. Based on my chemical formula, this is a 1-to-1 ratio. So the concentration of sodium nitrate being 1.5 molar means that I also have a concentration of nitrate that is 1.5 molar. Why don't you pause and see if you can do the same calculation on question 14. We'll write out 2.1 molar as 2.1 moles per liter. But we need to know the chemical formula of iron 3 sulfate. That's iron 3 plus, I said sulfate, but excuse me, that's sulfite. Sulfate is SO4 minus, sulfite is SO3. No, sulfate is SO4 2 minus, sulfite is SO3 2 minus. Similar to last time, crisscross method is needed here. So I get a chemical formula Fe2 SO3 3 for iron 3 sulfite. That's the chemical that I'm working with here. That's the concentration I know. And once again, I just need to do a mole to mole ratio. I need to get out of moles of Fe2 SO33, and I need to get into moles of Se3 2 minus. Here my mole ratio is not just 1. Instead, for every 1 mole of iron 3 sulfite, I have 3 moles of sulfite. My concentration is 6.1 molar. Notice how I get moles of sulfite per liter. 6.1 molar sulfite. Again, this can be written as 6.1 moles per liter of sulfite. Notice how we have a smaller concentration of a compound that has more units of sulfite. So I get a larger concentration of the smaller individual sulfite. If I'm going from a small value that contains a lot of pieces, I'm going to have a large value looking at the individual pieces. I believe we looked at number 15 in class. We looked at a dilution equation. So let's solve number 16 this time. In class, I pointed out that you can take the dilution equation, which can be written 2 different ways, kind of your preference. Do you like to think of it as molarity or generically as concentration? And you can pick out all of these individual pieces of information and you can write them down. C1, 1.0 molar. V1, unknown. C2, 0.1 molar. V2, 200 milliliters. Go through question 16 and see if you can't pull out those 4 pieces of information and find which one is the unknown. All right, a 50 milliliter solution with unknown concentration. C1, we don't know. V1, 50 milliliters, has been diluted to 150 milliliters with a concentration of 0.15 molar. C2, 0.15 molar. V2, 150 milliliters. Starting with my initial dilution equation, I can just run some simple algebra here so that I don't have to plug in my numbers and then move everything around. I realize I've made a mistake here. I want to divide by V1 so that I can get C1 on its own. C1, my unknown, is equal to C2V2 divided by V1. C1 is equal to 0.15 molar times 150 milliliters divided by 50 milliliters. It is true that molarity has embedded within it units of moles per liter. But it doesn't matter that my volume here is written in milliliters instead of liters, because molar is completely contained within here. Milliliters and milliliters cancels. I'm left with units of molar. This is just a simple calculator exercise. 0.15 times 150 divided by 50. My initial concentration was 0.45 molar. One thing we should check is that the initial concentration is larger than the final concentration. Dilution means concentration is going to get smaller. All right, with other types of concentrations, mass percent is going to be written as the mass of a component of a solution divided by the mass of the entire solution. Similarly, volume percent will be the volume of a component divided by the volume of the entire solution. And because these are percent per 100, we're multiplying by 100 to get these. This question is written where we know the mass of the component and the mass of the solution. I want to point out that the mass can be given in slightly different ways as well. For instance, if we knew that the mass was going to be total 200 grams, sometimes you'll be given that the mass of the water is 163.55 grams. So you know the mass of the component is 36.45 grams. You know the mass of the water is 163.55 grams. You'd actually have to add these together to recognize the mass of the solution, all things together, is 200. This is sometimes written as percent m over m, percent mass by mass. What I get here is 36.45 grams divided by 36.45 grams of HCl, and 36.45 grams plus 163.55 grams of water, or 200 grams of solution, multiplied by 100, 18.2% HCl. We do the same thing down here. This can be written as 100 milliliters of ethanol in 320 milliliters of water to make a solution, where we have to show that the volume percent is 180 milliliters of ethanol in 180 milliliters plus 320 milliliters to make the solution of 500 mils. 180 divided by 500. This gives a 36% ethanol solution. When working with ppb and ppm, similar to taking mass percent, instead of parts per 100, which is what cent gives us, we're looking at parts per million. So we look at our component over our solution, but this time we don't multiply by 100, we multiply by 1,000,000. For ppb, we take our component divided by our solution. We don't multiply by 100 or 1,000,000, we multiply by 1,000,000,000. 1 ppb is 1,000 times less concentrated than 1 part per million. If I have 1 part per million parts, I'll have 1,000 parts per billion parts. We can write this as a ratio. 1 ppm is 1,000 ppb. I'm looking at more parts with a billion, so I would have more individual things. So here we're looking at converting ppm to ppb. Well, this is a small number, not looking at a lot of things. I should get a larger number looking at more things. Let's see how it plugs in. 0.1015 ppm. If I have 1 part per million, that would be 1,000 parts per billion. ppm cancels. I multiply by 1,000. 101.5 parts per billion. In this second question, we're actually taking this calculation and we're working it backwards to find the mass of the component. I know that I have 0.1015 ppm of lead. That is some mass of lead in grams divided by a 100-gram sample, which is what I'm given, times 1,000,000. Remember that ppm and ppb are very, very small units of concentration. Something that is 1 ppm or 1 ppb is very, very dilute, which means I should not have a lot of mass of lead in this 100-gram sample. And that's going to become evident when I divide both sides by 10 to the 6th. That cancels my 10 to the 6th over here. On the left-hand side, we can write this as 0.1015 times 10 to the negative 6. Right now, it's actually not ppm anymore because I've divided by 1,000,000. But I don't actually have any unit here, so it looks a little awkward. On the right-hand side, I'm still left with an unknown mass of lead divided by 100 grams, which means now I need to multiply both sides by 100 grams. That cancels on the right-hand side, and here what I get is 10.15 times 10 to the negative 6 grams. When I multiply 100 grams here, I bring that unit with me. I move my decimal place to the right twice, but I'm not necessarily touching this other number. I could have only touched this other number and not moved my decimal place at all, or I can move my decimal place but not touch my exponent. This is the mass of lead, but you can see we're not actually following scientific notation. So to follow scientific notation, I'll move my decimal place to the left. That's actually getting me closer to 0, so my number is going to get smaller in the exponent, 1.015 times 10 to the negative 5th grams of lead. We could say this better. Let's write this in micrograms instead of just in regular grams. This is 10.15 micrograms of lead in that 100-gram sample. Not a lot of lead, but as it turns out, even small quantities of lead and other toxic chemicals can be incredibly dangerous. So regulatory agencies like the EPA, the Environmental Protection Agency, they set standards for concentrations of dangerous and toxic chemicals, and oftentimes you'll find that their maximum allowed concentration is something ppm, something ppb. That's because small amounts can make dangerous changes. Doing calculations and doing conversions takes a lot of practice, and it takes knowing your calculator well. So once you've gone through this sheet and you feel like you followed these steps, download a new version of it, clean, and try it again. Run through it until you're able to show these conversions quickly, until you're able to recognize what pieces of information you're given and how you can convert that into the pieces of information you need. Happy studying!